everyone, this is a video for class 30 of PH 125, and today we're going to be starting our discussion of fluids. Today we're specifically going to be talking about density, pressure, and buoyancy. Remember, the different states of matter are generally solids, liquids, and gases. So solids, remember, are objects that hold their volume and their shape. They're rigid, they have a fixed shape and a fixed volume. A liquid is something that holds its volume, it has a fixed volume, but it doesn't have a fixed shape. So remember, it can adapt its shape according to the container that it's in. Then we have gases, which adapt both their volume and their shape. So they take both the shape and the volume of the container that they're in. All right, and so then liquids and gases together are what we refer to as fluids. So a fluid could be either a liquid or a gas. Okay, so when we talk about fluids, we tend to talk about two quantities, density and pressure. So density and pressure, they're not just defined for fluids, but we tend to talk about them a lot when we're talking about fluids. So these apply to solids as well. When we talk about density, density is really just mass per unit volume. We use the symbol rho, so it looks like a script P kind of, it's a Greek letter. And so rho is equal to mass over volume, or m over v. The SI units of density are kilograms per meter cubed, and I have a chart of densities over here on the right-hand side. You can see I'll point out a few that we're going to talk about a little bit in this lecture. So the density of seawater, you can see it's a little bit more dense than freshwater. Seawater is about 1025, whereas freshwater is 1,000 kilograms per meter cubed. And air is far less dense, right? So 1.29 kilograms per meter cubed. All right, and then we also tend to talk about pressure when we talk about fluids, and pressure is really just force per unit area. It has the symbol P, which yes, is similar to power. I know we're recycling all of our letters at this point. So pressure, P, is force per unit area, or F divided by A, and the SI units of pressure, force is a Newton, right, and area is meters squared. So it's a Newton per meter squared, and we call this a Pascal, and so that has the symbol PA. So 1 Pascal, it turns out, is actually fairly small. Atmospheric pressure is 100,000 pascals. So a Pascal is a pretty small unit of pressure. Okay, and so then two really important properties of pressure. Pressure in a fluid acts in all directions equally at a single point. So a single point in space in a fluid, the pressure acts equally in all directions at that single point. And then the second property is that pressure will always act at a right angle to a surface in a stationary fluid. So in a moving fluid, we can have some variations, but for a static fluid or a stationary fluid, which is what we're talking about in this section, the pressure exerted on a surface by that fluid will always be perpendicular to the surface. So here you can see I have my little Nemo fish, and the pressure acting on little Nemo at each point in space is going to be perpendicular to the surface of him. Okay, all right. And so then atmospheric pressure, I already mentioned atmospheric pressure in pascals. I always remember it as 101.3 kilopascals. In other words, it's 1.01 times 10 to the 5th pascals. You might also see pressure in units of PSI. That's pounds per square inch. That's what PSI stands for. And so atmospheric pressure in pounds per square inch, or in PSI, is 14.7. All right, and so atmospheric pressure is really due to the weight of air above us. So the air in the atmosphere, its weight pushing down on us is what causes atmospheric pressure. And so with that in mind, we can actually think about calculating what is the mass of air above 1 square meter of the Earth. Okay, so to figure this out, we remember that P is equal to force divided by area. And so here, P atmosphere is equal to the weight of the air, so that's Fg of the air, divided by a particular area. So here that's going to be 1 meter squared. Okay, and so we can rearrange and solve for the weight of the air, and then we can solve that for the mass of air above the Earth. So Fg of the air, just rearranging, is going to be equal to A times P atmosphere. And then Fg of the air, remember, is just going to be the mass of the air times the acceleration due to gravity. So that's going to be equal to mg. Okay, so now we can solve for the mass of the air. M air is just going to be A times P atmosphere divided by G. Okay. And so then the area here is 1 meter squared. The atmospheric pressure, remember, is about 100,000 pascals. And then G is 9.8, so it's approximately 10. And so when we do this, M air is really going to be about 100,000 pascals divided by 10. So in other words, it's like 10,000 kilograms. Okay, so that's the approximate value of the mass of the air that sits above 1 meter squared of the Earth. And its weight pushing down on the Earth is what causes atmospheric pressure. All right, so that's really a lot of air, right? So it's hard to believe that there's really 10,000 kilograms of air over 1 square meter of the Earth, but the atmosphere extends really high above the Earth. And so it turns out there really is about 10,000 kilograms of air up there, which is just crazy. Okay. So anything that we think of having pressure above atmospheric pressure, we will tend to measure its pressure in terms of gauge pressure. So gauge pressure is really like the total pressure of a system minus atmospheric pressure. So just as an example, if you measure, for example, the pressure in your tires, what you're really measuring is gauge pressure, which is where it gets its name because it's what you would read on a pressure gauge. And so this is always like the pressure in the tire above the pressure of atmospheric pressure. So in reality, the pressure inside the tire is going to be equal to whatever you measure plus the atmospheric pressure. But because atmospheric pressure is always around and it's always constant, it's always just this 101.3 kilopascals, what we're really generally interested in is actually this gauge pressure. So P gauge is really equal to the total pressure, for example, in a tire, so total pressure in a fluid, minus atmospheric pressure. So just a few examples here. If you think about a car tire, which has a gauge pressure of 29.4 psi, well, we know that the atmospheric pressure is really 14.7 psi. And so actually the total pressure in the tire is going to be the gauge pressure that you measure, so that 29.4 plus atmospheric pressure, which is 14.7. So the total pressure in the tire when you read 29.4 psi on your gauge is actually 44.1 psi. All right, if you have a flat tire, that's when your gauge pressure reads 0 psi, but really you know that your tire is actually at atmospheric pressure. And so then the total pressure in the tire is just going to be 14.1 psi. So that's atmospheric pressure. It acts on us all the time. All right. So quick question here, a little thought question. If you have two containers that are filled with water, they're identical containers, but the first one's completely full and the second one is half full. We want to know, how do we compare the pressure that each container exerts on the table? Okay, so in this question here, we have to remember that pressure is equal to force divided by area. The force exerted by the cup on the table is going to be due to the weight of the cup, which will be equal in both cases, and the weight of the water in the cup. So really what we're interested in is the weight of the water in the cup. So in this case, the weight of cup 1 is going to be greater than the weight of cup 2 because cup 1 is completely full, whereas cup 2 is only half full. All right, so that means that there's going to be a greater force acting on the table due to cup 1. And then we have to think about the area over which that force is acting. So the area over which it's acting is going to be like the surface area of the bottom of the cup. But here we're told that the cups are identical, which means those surface areas are going to be the same. And so what that means is that cup 1 is going to have a bigger F divided by the same A compared to cup 2. And so the pressure exerted on the table by cup 1 is really going to be greater. So I would pick answer C here. Okay, so now we want to think a little bit about how pressure varies as a function of depth. So it turns out that pressure at a particular distance below the surface of a liquid will be different than the pressure at the surface of the liquid. And we want to figure out how pressure changes with depth. So here I have atmospheric pressure at the surface of my cup. Remember, everything in the atmosphere is going to be subject to that atmospheric pressure. So whenever you have a fluid in an open container, that means that the open part is going to be exposed to atmospheric pressure. So the pressure right at the top of my fluid level in the cup is just going to be exactly equal to atmospheric pressure, PAT. All right, and now our goal is to find P here, which is the pressure at a distance h below the surface of the cup. So how do I go about doing that? Well, really, that pressure is going to be equal to the atmospheric pressure plus the additional pressure due to the weight of the fluid that sits right above my new line where I want to measure the pressure. So this is really the weight per unit area of the fluid from the surface of the cup down to location H. So it's the light blue shaded volume that I have shown over here. The weight of that volume of fluid is what contributes to an additional pressure at location P, above atmospheric pressure. All right, and so then the weight of that liquid, this is just like what we did when we talked about the weight of the air that causes atmospheric pressure. It's the same idea here. So the weight of that liquid that sits on top of location P is just going to be m times g divided by A, where A is like the surface area of the fluid in our cup here. Okay, and so then m we can actually relate to density and volume. So in terms of fluids, it's generally less straightforward to think about mass than it is to think about density and volume. It's usually easier to measure density and volume than it is to measure mass in a fluid. And so a lot of the times when we're talking about fluids, we'll try to replace mass with density times volume, which comes directly from the fact that density is equal to mass divided by volume. So just rearranging, we get m equals rho times v. Okay, and so then that's going to be the volume of that fluid, the light blue fluid that's sitting on top of our point P here. Okay, so all I've done now is I've just plugged in rho times V for m. And then the last thing I need to do is recognize that that volume of fluid, this light blue volume of fluid, it's really equal to the surface area of the fluid times h, the height of that fluid column. So that's how we would calculate the volume of fluid that's sitting on top of point P here. And so just replacing V with A times h, then I see that my A's really cancel out and I'm left with P atmosphere plus rho GH. So the pressure P at distance h below the surface is just equal to the atmospheric pressure plus rho GH. Okay, so that is super useful, and we can think about a classic example application of this principle here. If you think about a U-tube, so not like internet YouTube, but literally a U-shaped tube filled with some fluid, it turns out that if you are at the same depth in that U-shaped tube, it doesn't matter where along the depth of a fluid you are, as long as you're at some constant depth relative to the surface of the fluid, the pressure will be the same. So what that means, if you have a container that's open to the atmosphere, then the pressure at any depth is always going to be the same regardless of the shape of the different arms of the container. So here the pressure is the same for each of the different arms in our kind of silly looking container over here. We have the thin one, you have the one with the bulbs, the curly one, and then the fat one. It doesn't matter, everywhere along that red dashed line the pressure is going to be the same. So it's really tempting to think that it should change because pressure is related to force and area, and the areas are changing. But actually, as a result of this equation that we derived up here, when you're at one constant height, the pressure is always the same, regardless of how big the tube is or the shape of the tube or anything like that. Okay, so that's why if you're in the ocean and you swim at a constant depth relative to the surface, the pressure will be the same everywhere. All right. Okay, and so now we want to expand this definition. So we know how to find the pressure at a given height h below the surface of a fluid. And now we want to think about what about relative pressures between 2 points within a fluid. So not just from the surface to some particular point, but between 2 points in a fluid. So this would be a more generalized result. Okay, so here I want to know what is pressure P2 relative to the pressure P1 as drawn on my little cup here. You'll notice P1 is a height H1 below the surface of the cup, and P2 is a height H2 below the surface of the cup. Okay, so from our last equation, we know that P2 is going to be equal to the atmospheric pressure plus rho GH2. And then what I can do is I can define H2 in terms of H, which is the distance between the location where I'm measuring P1 and the location where I'm measuring P2. And then I can also relate it to H1. So just looking at this diagram here, if I want H to be the distance between where I'm measuring P1 and P2, then H2 is going to be equal to H1 plus H. All right, and so I'm going to use that in my P2 equation that I have over here on the left-hand side. I'm just going to plug in for H2, that H2 is really equal to H plus H1. Okay. So then with that in mind, rho times G will get distributed to both the H and the H1. And what I get is P atmosphere plus rho G H1 plus rho G H. Okay, and the way I wrote it out, hopefully we recognize that P atmosphere plus rho G H1, that's really the pressure at location 1. And so then what I'm left with is just P2 equals P1 plus rho G H. So P2 is the pressure at a distance H below P1. Really important, I have it in bold here. It's below. So if instead P2 is being measured above P1, you would want to plug in a minus H. If it's being measured below, you use a positive H. Okay. So that's kind of a little tricky thing about thinking about this equation. I usually just define my pressures so that P2 is always the pressure that's being measured below P1. All right. And so how do we measure pressure? This is the next question. And so it turns out we actually use the principles that we just talked about. So the fact that pressure varies with depth. And so the instrument that we use to measure pressure is a barometer, and this is how we measure atmospheric pressure specifically. All right, so the basic idea behind a barometer is that you have a tube that's filled with liquid, and then you invert that tube inside like a dish that contains the same liquid. Okay, and so then what will end up happening is the liquid will flow from the inverted tube out into that dish until it reaches some sort of equilibrium. And when equilibrium is reached, what will end up happening is we will get a relationship between the height of the column of liquid in the tube and atmospheric pressure. Okay, so important things to note. The tube was completely full of liquid. You invert it, so we end up getting a vacuum in the region of the tube above the liquid. So everything above the liquid is a vacuum. There's no matter up there. And so then the pressure is going to be 0. There's nothing exerting a force on the surface of the fluid up inside that tube since there's a vacuum in there. So the pressure up at this marked location for P1 is going to be 0. All right, and then the dish that inverted tube sits in, it's open to the atmosphere. And so that means that the pressure P2 at the height of the fluid that's in that dish, that's just going to be atmospheric pressure since it's open to the atmosphere. All right, so with all of that in mind, we can just use the equation P2 equals P1 plus rho GH. Here, P2 is below P1, right? So that's good. We want P2 to be the pressure below P1, and it's below P1 by a height H. P1 we know is just 0, right? We said that's because there's a vacuum. And so P2 is equal to rho GH. All right, and P2 we said is atmospheric pressure, which means that now we can solve P atmosphere is equal to rho GH for this barometer setup. And what that means is that we can go ahead and measure the height of this column of liquid. If we know its density, we can easily calculate the atmospheric pressure. Okay, and so traditionally these barometers were made with mercury. And so when a barometer, that's the fluid that was in it. So when there's a barometer that's filled with mercury, it turns out at atmospheric pressure, the height of the column of liquid tends to be 760 millimeters. So this is why you might actually see pressure measured in terms of millimeters of mercury, and atmospheric pressure in terms of millimeters of mercury is 760. So this is an alternative measurement of pressure. 101 kilopascals is equal to 760 millimeters of mercury. Okay, so now I have kind of a fun question for you guys to think about. I want to know if you stand on the roof of a 5-story or 50-foot tall house and try to drink using a straw from a glass, can you do it? Okay, and so this might seem like I have no idea where to start on this question, so I have some hints. First of all, if you are sucking on a straw, you would suck all of the air out of the straw. And so you would create a vacuum in the straw between like your mouth and any fluid that would be in the straw. So there is no air in there to create pressure at the top of the straw. And then my next hint is to think about what is the pressure at the surface of the cup. My last hint that I forgot to write out here is that 1 meter is approximately 3 feet. So that's one last thing that you might need to know. All right, so I'll let you try to think about it for a second. So the real question is to think about how high will the water rise if we consider this straw to be like a barometer. So it's like a barometer because we know if we think about the pressure up here, let's call that P1 because it's going to be above our pressure down here, which is P2. And we know that P2 is equal to atmospheric pressure because the cup is open to the air. So P2 is going to be P atmosphere. P1 we know is going to be equal to 0 because just like a barometer, you've sucked all of the air out of the straw and so there's a vacuum up there. And so since there's no mass pushing down on the straw, there's no pressure in there inside the straw. So P1 is just going to be 0. All right, so then we're left with P2, which is equal to P atmosphere is equal to P1 plus rho GH. Okay, P1 is 0 here, and so we're really left with P atmosphere is equal to rho GH. And so we want to calculate how high is it possible to get the water to rise or the fluid to rise in the straw. So I can solve for H here. H is just going to be equal to P atmosphere divided by rho times G. Okay, so P atmosphere we know is equal to 100,000 pascals. And then we have rho, which is the density of water. That's 1,000 kilograms per meter cubed. Okay, and then lastly, we know G, let's use 10. Oh, sorry, meters per second squared. I'll be good and use units. Okay, so then we get cancellation of 1 0 with that guy. Let's cancel 3 more zeros. Okay, and so the height is going to be equal to about 10 meters, which is about 30 feet, if you think about there being 3 feet per meter. So the maximum height that you could get the fluid to go up in the straw is about 30 feet. So 50 feet is probably out of reach. So probably not going to get any water up the straw at a 50-foot height. If you were at 30 feet, okay, so maybe only 3 stories, you'd be all right. Okay, so kind of silly, kind of fun. But the answer here is no. Okay, so the last principle that we're going to talk about for today with respect to fluids is Archimedes' principle. So as the legend or the story goes, Archimedes was commissioned by King Hero to determine whether or not his golden crown was real or fake. So he suspected that it was fake and he wanted Archimedes to figure out whether it was truly real or fake. And so the principle that Archimedes exploited to determine whether or not the crown was real was the buoyant force. So we'll circle back to the crown. We'll talk about it after we talk a little bit more about the buoyant force. So the buoyant force, FB, is really the net force of the fluid acting on an object that's in a fluid. So we can think about it as just being whatever forces the fluid is exerting on an object that is suspended or it's inside of that fluid. Okay, and so I call it F net F. And the way to think about this buoyant force is to remember that in a fluid there is pressure, and so the pressure acting on the object is going to be related to the forces exerted on the object by the fluid through the relationship that P is equal to F divided by A. And so then the force acting on an object is going to be equal to the pressure at that particular location where that force is acting times the area over which that force is acting. Okay, and so here I have a cube that's suspended in some sort of fluid. So we'll say that the fluid has density rho and my cube has surface area A. So each side of my cube has area A here. All right, and so then our goal is to think about what is the net force of the fluid acting on this cube. And so if you think about it in terms of the forces acting on the cube, all of the arrows that are in the horizontal direction, those forces acting due to the pressure at those different locations, it will all be canceled out because it's at the same height. And so only differences in height lead to differences in pressure, which lead to differences in the forces acting on the object in the fluid. So really only this top arrow and this bottom arrow will be not completely balanced because those are acting at different heights, right? So one is acting at height h1 and the other one, the bottom one, is acting at height h2. And so we can use this information to think about the net force acting on the object. So here, remember that the pressure is going to be higher at location 2, right? So it's higher when you're lower in the fluid. And so I would expect the force due to pressure 2, so let's call that F2, I would expect it to be pointing upwards, right? Because it's perpendicular to the surface of the object, and it's also going to be greater than F1. So with that in mind, then we can think about the net force of the fluid acting on this object. We're going to have F2, which is pushing upwards, and it's bigger than F1, which is pushing downwards. And so then the net force of the fluid is just the sum of those two. So since F1 is down and F2 is up, that's going to be F2 minus F1. And that net force is really just equal to the buoyant force. Okay. So with that in mind, we have F2 minus F1, and then I'm also using the relationship that the force is equal to the pressure at that location times the area over which that pressure is acting. So here A1 is going to be equal to A2 because those are just the surface areas of our cube. Okay, and so then what I can do is I can say, okay, A1 is equal to A2, and those are both just A, that's the surface area of the cube on each of its faces. And I can plug in the fact that we know P2 is really going to be the atmospheric pressure plus rho g H2, and P1 is really going to be atmospheric pressure plus rho g H1. So I've just taken that and plugged it in for P2, and then also for P1 down here. Okay, so now I have another little equation, and we have factors of P atmosphere that will cancel, right? So I have P atmosphere minus P atmosphere, those will cancel. Rho, G, and A are the same between my first term and my second term, so I can factor those out, and I just end up with rho G A times H2 minus H1. Okay, and so then with that in mind, H2 minus H1 is really like the total height of one side of the block. A is the surface area of the block, and so really H2 minus H1 times the area is just going to be equal to the total volume of our little cube here. Okay, so I can replace A times H2 minus H1 with V, the volume. Okay, and so with that in mind, then I get the buoyant force is equal to rho G V. So rho is the density of the fluid, G is the acceleration due to gravity, and V is the volume of the object that's submerged in our fluid. Okay. All right, so this is our buoyant force. It's the net force of the fluids acting on the object. And I'm just going to kind of switch around the notation a little bit. It's exactly the same formula. I've just added some subscripts because we're going to talk more about different volumes and also different densities. And so it gets a little confusing if you don't really specify which density and which volume you're talking about. So the buoyant force is equal to the density of the fluid, rho F. I'm calling rho F the density of the fluid, times G times V sub. Sub means submerged. Okay, and so then a way to think about this buoyant force is to think about the density of the fluid times the volume submerged of your object. And so if you think about having like a really full glass of water, and then you place an object with a particular volume in that glass of water. So whatever volume of your object sinks under the water, the amount of water that gets displaced, so the amount of water that would flow over your surface of your cup, it would have exactly the same volume as the volume of your object that ends up getting submerged in the water. And so what that means is that the volume that's submerged times the density of your fluid, that really corresponds to the mass of your fluid that gets displaced by your object, right? Because really, V submerged is equal to the volume that gets displaced. So that's the displaced volume of water. And so, or fluid, it could be any fluid, sorry, I think I keep doing that. And so then V sub is equal to the volume that gets displaced multiplied by the density of that fluid, and that gives you just the mass of the fluid that gets displaced. And so this is kind of a general way to define the buoyant force. We say that it's really the weight, because weight is going to be mg. So if you look here up at the top, rho F times V sub, we said that's replaced with mF, so really FB is equal to mF times G, right? So the mass of the displaced fluid times G, or in other words, that's going to be the weight of fluid displaced by the object. So now we're ready to circle back to Archimedes and his crown. Well, not his crown, Hero's crown, because I know you guys are all just dying to find out if the crown was a fake, right? Okay, so anyway, the basic idea that Archimedes came up with, supposedly he thought about it when he was taking a bath. His idea was that if he had some mass of gold, which we thought the crown was gold, right? So if he had some mass of gold that was exactly equal to the mass of the crown, then if the crown and the gold have the same density, in other words, if the crown was also made of gold, then when he placed each of them into a really full bucket of water, they would displace the same amount of fluid because they would have the same density, which means they would have the same volume. So the key here was that you can't measure the volume of a crown very easily, right? It would be really hard to calculate. So he needed a way to figure out the volume of the crown, which is related to the density. All right, so the idea was he placed, this known mass of gold, and then he placed the crown, which had the same mass, in a bucket of water, and it turned out that they displaced different amounts of water because the crown was, in fact, it was not gold. So it had been mixed with silver, which was cheaper, and so anyway, he exposed the fraud, right? Okay, so there's a little story to go along with this information. Okay, so now let's just do a quick practice problem here with buoyancy. So we have an iceberg that's in the ocean and it has a density of rho ice, and the total volume of the iceberg is V ice, and we want to know what is the buoyant force acting on the iceberg. Okay, so we're going to assume that this iceberg is floating in the water, and so since the iceberg is floating in the water, that means that it must be in equilibrium. So what that means, it's not accelerating upwards, it's not sinking to the bottom, it's just floating. And so that means that the net force acting on it in the y direction must be 0, right? It's in equilibrium. Okay, so with that in mind, we can think about the net force acting on it in terms of the sum of all the forces acting on it. So we know that the water that it's floating in, the fluid that it's floating in, is going to act on it with a force FB, right? That's the net force of the fluid acting on an object is the buoyant force FB. So that's going to be acting, pushing up on the object. So that's FB, or in other words, F net of the fluid acting on the iceberg. Okay, then the other force that this one is counteracting, or it's balancing, is really the weight of the object. So that's going to be Fg of our iceberg, the weight of our iceberg. Okay, so then our net force, it's equal to 0 because acceleration is 0, and we know F net is equal to mass times acceleration. And then we know F net is also equal to the sum of the forces acting on our iceberg. So that's going to be the buoyant force upwards, Fb, minus gravity downwards, Fg, so minus its weight downwards. Okay, and so with that in mind, we can solve for Fb. Fb is really just going to be exactly equal to the weight of the iceberg in this case. Okay, and so then we can think about Fg, the weight of the iceberg. We know Fg is going to be equal to the mass of the iceberg times g. We don't know the mass of the iceberg, but we are told its density and its volume. So remembering that rho is equal to m divided by v, we rearrange and get m is equal to v times rho. Okay, so then we can rewrite this. M ice is equal to rho ice times v ice, and we get Fb is equal to rho ice, v ice, which is the total volume of the iceberg, times g. Okay, so that is our answer to question A. And now question B, we want to know what percentage of the total volume of the ice is submerged. So for this, we need to think back to our other definition of the buoyant force, or our definition of the buoyant force that we came up with last slide, which is that the buoyant force is equal to the weight of the fluid displaced by the object in the fluid. So here that means that Fb is going to be equal to, remember, it's the density of the fluid times the volume submerged, right? So that's really the mass of the fluid displaced by our submerged object. And that is multiplied by g so that we get the total weight of the fluid displaced by our object. Okay, so with that in mind, we can set that equal to FB, which we found up above in terms of the density of the ice and the volume of the ice. So we say this is going to also be equal to rho ice, V ice times G. We have G's on both sides, those cancel out. And what we're looking for is the percentage of total volume of the ice that is submerged. And so what that really is going to be is V sub divided by V total, so the total volume of the iceberg, which is V ice. Okay, and so we can find that by rearranging this equation we have up above. We need to divide both sides by V ice, and then we have to divide both sides by rho F, and we end up getting rho ice over rho F over here on the right-hand side. And so then we know rho ice, it's 917, and the density of the salt water is 1025. And so when I plugged in those numbers, I got 0.89, or in other words, 89% of the iceberg is going to be submerged. Okay, if I were to ask for instead the volume above the water, remember you would have to subtract 1 minus that 0.89 to get the volume above. Sometimes there are some tricky little things like that that happen. Okay, so that's how we would find the volume of, or the percent volume of the iceberg that is submerged. And really this result that we came up with it's a completely general result. And so whenever we are thinking about a floating object, so not something completely submerged, but something that's floating, the volume of that submerged object is always going to be equal to the total volume of the object multiplied by the ratio of the densities. So the density of the object divided by the density of the fluid. Okay, so we're going to do some more practice problems with this in class, but that wraps up the video for today. This also completes the material that will be covered in exam 3. So I will see you guys in class.